In this video, we will continue investigating how we can come up with a power series representation of a given function. Recall from our previous videos, our method for doing so had been to somehow compare with the power series representation of 1 over 1 minus something. And 1 over 1 minus something can be represented as the sum from n equals 0 to infinity of that something to the nth power, and it converges whenever the absolute value of that something is smaller than 1. Now, when this approach works, it typically works well. You compare to this formula via algebraic manipulation or calculus, i.e. differentiation or integration. However, we are not always able to do so, or it is just not convenient to do so. It turns out that there's a more analytic approach. If you have a power series representation of a function, and note this is a power series centered at A, then the coefficients c sub n must have the following formula. C sub n will be the nth derivative of the function evaluated at A divided by n factorial. And what this tells us is instead of trying to manipulate and relate back to some known formula, we can generate the formula ourselves by trying to determine a pattern for what the value of the nth derivative will be evaluated at A. Now, a bit of language here. If A is 0 and we have a power series centered at 0, we will refer to this as being a Maclaurin series. If A is not 0, we will call it a Taylor series centered at A, and this is typically the formula we think of associated with a Taylor series representation of a function. So let's look at a very common example. Let's find the Maclaurin series for f of x equals sine of x. So recalling from our previous slide that power series representation would be sine of x is going to be the sum from n equals 0 to infinity, and then we're going to use our formula for the coefficient. So this will be the nth derivative evaluated at 0 divided by n factorial times x to the n, where in this case our function f of x is sine. And if we think about what we actually need to have this power series representation, the x to the n factorial, those are things that are not going to change. They're there. What we need to determine is what is the nth derivative evaluated at 0. And that's something that we are hopefully very good at, differentiation. So let's just go ahead and calculate a few quick derivatives. So f prime is cosine. F double prime is now minus sine. F triple prime is minus cosine. And when we take the fourth derivative, we simply end up back where we started. We're at sine. So it keeps going. And what we need to do is evaluate at 0. So f of 0 is 0. Cosine of 0 is 1. Sine of 0 is still 0. Cosine of 0 is 1, and because of that minus, we get minus 1, and so on. So what we see is that if we have a derivative, which is an even derivative, that would be the function itself, second derivative, fourth derivative, sixth derivative, so on. That nth derivative at 0 is going to be 0 for all of the even derivatives. So the only terms that we are going to have present in our power series representation for sine will be the odd terms. And in terms of representing an odd number, we can do so by replacing with a 2n plus 1. So all of the odd terms would be represented as seen here. Because note, what is an odd number? It's an even number plus 1. If you plug in n equals 0, that corresponds to 1. If you plug in n equals 1, that corresponds to 3, and so on. Now for the nth derivative evaluated at 0, the first derivative we get back 1, the third derivative we get back minus 1, the fifth derivative it's going to be 1, and so on. So it's either plus or minus 1. Which means the formula is going to be minus 1 to a power. And we want to make sure that when we plug in n equals 0, we get back 1. And I say n equals 0 because that corresponds to the first odd number. So the formula is going to be either minus 1 to the n or minus 1 to the n plus 1. And because we want to get back a positive when we plug in 0, the formula is going to be minus 1 to the n. And this is the Taylor series, the Maclaurin series for f of x equals sine of x. And if you wanted to write this out without the summation, you can think of this as being x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on. In terms of a bit of intuition for remembering this formula, recall from both pre-calculus and calculus, sine is an odd function. And what that means is that the graph of sine is symmetric about the origin. Also note that the only powers present in this Maclaurin series representation for sine are the odd powers, which is how we can remember this formula. Now to add to our maybe list of common power series representations that we should make sure to remember. And now we can actually call these what they really are. It's a list of common Maclaurin series. So the first formula and then the fourth and the fifth are formulas we've previously encountered. Adding to that list would be the power series representations for cosine and sine. In the previous slide, we've come up with a power series or Maclaurin series representation for sine, and note that for cosine they're extremely similar. The only difference is that with cosine, which is an even function, you only have the even powers present. So thinking about sine as an odd function, cosine as an even function, is really good intuition in terms of remembering these formulas. So let's investigate another example where here we'll find a Taylor series representation for the exponential function centered at a equals 1. So recalling the formula, if it's centered at 1, we want to represent this as the sum from n equals 0 to infinity of the nth derivative evaluated at that a value, divided by n factorial, times x minus 1 to the nth. And whatever value a we are centering at would be plugged into the nth derivative and then x minus a. Once again, the x minus 1 to a power, the n factorial, those are going to be there. That's not a changing quantity. What we need to determine is a formula for the nth derivative at 1. And this is typically where the difficulty lies. Do we have the differentiation and pattern recognition capabilities to come up with that general formula? This example works out very conveniently. The derivative of e to the x is always e to the x. That is, it doesn't matter whether it's the first derivative, the second derivative, or in general the nth derivative, it will always be e to the x. And what we need for our formula above is the nth derivative evaluated at 1. So e to the 1 is simply the number e. So we can take e and plug it in to our Taylor series. This would become the sum from n equals 0 to infinity of e over n factorial x minus 1 to the nth power. So this is a Taylor series representation of the function e to the x centered at 1.